Hi there, it's Matt Heffernan. Welcome back to my channel. I know it's been a while since I had a video out, kind of took off a week, and this is going to be another kind of quick one. I've got a lot of stuff that's cooking, and as you can probably tell by this thumbnail and title screen, that one of the things I'm working on is a new 8-bit architecture. I'm actually going to design my own 8-bit processor based on a few goals and ideals that I have. So let's get right into that. What is it? What is ROCKET88 going to be? Well, my first goal is going to be a simple RISC-like instruction set. Now, this is obviously not going to be a modern RISC type processor. This is not like an ARM processor with all sorts of fancy pipeline and everything. This is going to still be a very straightforward single pipe basic 8-bit processor, but I want to make sure that the instruction is very simple, not a lot of falderall, not kind of like the Z80 where there's a million different opcodes and everything. And then the main way I'm going to help constrain that is making sure that all the opcodes are only 8 bits. None of these 16, 32, so on bit opcodes like you get with the Z80. So there's going to be fewer than 256, and in fact, quite a bit fewer. And another thing that I think is going to be really helpful for this is to have a consistent use of addressing modes, especially as they relate to the arrangement of the opcodes in that opcode table. So I want to make sure that when you use an instruction that it is going to work in the way that you would expect it to, because it doesn't have a lot of weird exceptions. It just kind of works the way that other instructions do in that instruction set architecture. And of course, above all, keeping it simple, stupid. Just make sure that I'm not adding anything really unnecessary to this instruction set, that it's going to be simple to implement and debug and get up and running. That's going to be the real big thing. And in fact, some of the stuff that I already have sort of planned out for it, I think is still very much unnecessary, but it is born out of this goal of having that consistent use of addressing modes, and we'll see that soon. And then the other big category of goals are a fast FPGA implementation. I'm obviously not going to manufacture this. What I'm going to have is an open source Verilog, or maybe VHDL, but more likely Verilog because that's the tool set I have right now. Make that implementation open source, sharing that with the community. And so that if you want to have your FPGA have a core that is a ROCKET88 core, you can go right ahead and do that. If you think some of my implementation sucks, you can go right ahead and do a pull request and make it work better, and you can test it on your own system. That's going to be kind of the beauty of this. So one of the goals within that implementation, since it is FPGA, I don't have to necessarily worry about the layout of the silicon or a particularly constrained number of gates. I'm more about constraining the number of logic units to it, is making sure that this instruction set is going to be able to fetch and decode these instructions as quickly as possible, that it's a very simple to decode instruction set. We're not spending all these cycles just figuring out what the instruction is going to do. And so because of this, then we should want to minimize the cycles per instruction. So once it's fetched and decoded, that there's not a lot of internal steps. There's not going to be an LDIR that can run for like a minute straight. It's going to be a very small number of cycles so that we're getting a lot of bang out of our buck, as it were, from the clock. So that's all I really have for now. I'm going to get into more of a formal presentation on what this architecture is going to be. But for right now, let's go right to this spreadsheet that I have. So this is the only form in which ROCKET88 exists right now. I haven't written any of the Verilog yet. It's more sort of in my head, and I've used this spreadsheet to help start defining what that's going to be. And of course, nothing is set in stone. In fact, that's going to be the beauty about this being an open source Verilog implementation of a CPU, is that there's not going to be just one version set in stone. It's going to work that way forever. Eventually, we'll have sort of a standardized version of this instruction architecture, but there could be multiple different implementations. And of course, I will be taking pull requests from the community. So, things will change, but eventually the goal is to have it stabilized and make it work in a way that's going to be consistent. And of course, part of this whole open source deal is going to be the assembler for it, to make a cross-platform platform independent assembler. I don't even know necessarily what language I'm going to use to write that assembler in, but it's going to be something that is going to be accessible easily for people on different platforms. And so, that might be C, it might be Python. I have yet to really figure that out. Maybe I'll do both. Who knows? Because the point is, the assembler is going to be pretty simple. If initially just a basic assembler, and it's not necessarily going to have a ton of macro features and all that, just going to be kind of straightforward at first. And of course, it'll evolve from there. But again, it's going to be a fully open source architecture. There's not going to be any sort of intellectual property barriers to folks creating their own tooling for it. And so here's what the general architecture is in terms of what's going to be in the CPU. Now we're going to have a single 8-bit accumulator. This is still very much an 8-bit processor, just like the old ones from back in the 70s and 80s. But I'm like the Z80, I'm going to have a couple of general purpose registers, and they're going to be B and C. And like the Z80, B and C will be combinable into a 16-bit address register, which we'll see how that's going to work once we get into the instruction set a bit. And then a couple of additional address registers in there. Of course, we need to have a program counter, and we're going to have 16-bit addressing, so that'll be a 16-bit program counter, and we'll also have a full 16-bit stack pointer, because we don't want to mess around with an 8-bit stack pointer like you have in the 6502. That's so annoying and counterproductive and limiting that no, we're going to let you have a stack as big as you want within that 64K memory space and place it wherever you want. You want to make the whole thing a stack? Go right ahead. So then the only other quasi-register we're going to have is the P register, which of course is a program status. And it's going to have all these different status bits, and we're going to get into what those are, but it's all the usual suspects for status bits. And like pretty much in these 8-bit registers, we're going to have 3 vectors in memory for interrupts and other events. So you'll have our standard maskable interrupt vector will be at the end of memory, followed by the NMI vector, the non-maskable interrupt, and of course a reset vector at the very, very end. So those last 2 bytes in the memory space are going to be the reset vector that is generally going to be hit when you power something on. That would be the recommended implementation, is to start with a reset. And then after that, just some basic pins. There's probably going to be more pins that I'll need to add in there, but again, keeping it very, very simple. So of course we'll have our, our voltage, our like 5 volt or whatever it's going to be. But it doesn't really matter what the VCC is. This is 3 volts, 5 volts. It's going to just be an FPGA thing. So these pins are like, okay, we're sort of pretending it's going to have this voltage and ground pin. And then it's going to have for actual input, for data input, of course, there's going to be a clock. And we want to make sure, obviously, that clock can run as fast as possible. And then we'll have the IRQ, NMI, and reset pins for triggering these different vectors. So basically, if we get IRQ, it has to be an enabled event since it's maskable. And if it is enabled, it's going to push all of these registers to the stack, except for the stack pointer, obviously. And then it is going to jump to the address that is going to be stored at this FFFA. And then the same goes for NMI. Of course, that's non-maskable, so that's always going to happen. And the same for reset. Reset is non-maskable, and it's just going to do a straight jump without pushing anything to the stack to FFE, assuming that the stack's going to be blown away and reset anyway by whatever code is at the address that is stored there. Then for output, we're going to have 16 address pins and read and write pins. And then for a little bidirectional action, of course, will be an 8-bit external data bus. And that's pretty much it. Whether we need anything beyond that's going to come up once I start actually implementing a simple computer around this. So taking a quick look here at the instruction set, you can see it's a fair number of instructions, but 231 with a bunch in the middle here with these other rows and blanked out bits, so little blank spaces within the opcode table. But that's it. Those are all of the opcodes. And you can see here they look kind of familiar. If you have to do the 6502, you'll recognize LDA and, of course, NoOp and pretty much everything, and store A and push A and pull A. So all of these things are in there, but they're placed in a very specific location within the opcode table, and that's better explained by first going here to the opcode breakdown. So here's the way opcodes are going to be encoded. Based on the high nibble, that top 4 bits is going to determine what sort of operation it is. And if those top bits are between 0 and 14, it's going to be one of the standard, quote unquote, standard instructions that in each of them use all of the different addressing modes. Now, obviously, some of these addressing modes don't make sense to use in some of these cases, and that's where we do a little bit of fill-in here and there, where it's something along the same lines that it would take a small amount of logic to be able to switch to this other interpretation of the opcode. So right at the very top, if that upper nibble is 0, it's going to be a no-op, no matter what. No matter what happens, if that upper nibble is 0, it's a no-op. It gets treated as such. If it's a 1, it's going to load or store the A register. And now we can consider what are the source or destination of this. So we can see here if the next bit 3, is a 0 for 0, 1, 2, or 3 in these top bits, we're going to be loading to a register. But if it's 1 here in bit 3, we are going to be storing from a register into memory. But here, if we have one of these store to register, say we're not going to do store A to A or store A to B, for instance, because we can always do the reverse load for those. So instead of storing to register, those are going to be compare instructions. So that's one way where we're sort of shoehorning in things. But then the lower 3 bits are going to determine the addressing mode. And we're going to have a 0 addressing mode, which is an immediate value. So here, this is, especially when we're talking about loading, this is loading a 0 directly into a register, so that it's going to be an opcode for loading 0 someplace. So, very useful thing to be able to do is just zero out a register with a single 8-bit opcode. And then otherwise, we're going to have a 1, 2, or 3 would be the A, B, or C registers for the source or destination. So we'd know then if we are going to, say, load the register A with B, we're going to have a 1 here. We're loading to the register, loading to A, and then we are going to have 2 here for B, load A with B. And that's how it kind of works. So then here, if this bit was 1, these are going to be stores. So then we could have here, say if it's 2, it's store B. So the 1 here from B, and then we're going to store B into some other place. Now, obviously, we're not going to be able to store into these. That's why here, if we're storing to a register, this is going to be a compare. So it'd be like compare B with A or C. But if it's 4, that's immediate. That's nonsensical. Then 5 would be an address. So they'd be storing to an address, for instance. So let's backtrack yet again because I'm kind of getting ahead of myself. So let's go back again to say a load. So for having a load instruction here, it's going to be 1, 2, or 3, and here is going to be 0. So loading to a register, and so say if it's 1. So again, like we saw before, load A 0. So loading into A, and then 0, 0. A, B, or C, but then we get into these other addressing modes. We'll have the immediate addressing mode here if it's 4, so that means there's going to be another byte after the opcode with an immediate value to load in that register. If it's 5, then we know there's going to be a direct absolute address that's there, and so there's going to be 2 bytes after the opcode for that address, and we're going to keep it little endian. We're going to keep it little endian to make it more like the 6502 or the Z80, so we're not being too different there. And also, a lot of times, little endian does make sense when you get down to things. And then we have for an addressing mode, this is something similar to what you see in the Z80, which is a 16-bit register indirect. So what we can do is in the B and C registers, we can load an address into B and C, and then use that address as is what we're going to say load or store from. And then, of course, we can do the same thing if it's 7 with the stack pointer. So when we're talking about a load or a store to the stack pointer, obviously that's the same as like pushing or pulling from the stack. So that's how it's all going to work. This is how we know basically what we're going to do, what register we're dealing with here, and then which direction the data is going, and what sort of addressing then we are doing for an operand. So very, very simple. Even though in some cases it doesn't make a lot of sense to do things in a certain way, like why are we taking up space in the instruction set in the opcode table with instructions that will likely never be used? Well, the point is that, yeah, sure, we're taking up space per se in the opcode table, but we are also creating something that's very simple and follows the same pattern over and over again, so that it just makes the wiring of it simple. So it's not a dead space in the opcode table. It's still going to have a very specific effect, and it will also help to sort of do things with macros or compilers, so that you don't have as much guesswork or special cases like, oh, if we change this source or destination, is that going to be there? And then we can know that the answer is going to be yes. It's going to be there because we're trying to keep this consistent. And but then, of course, things kind of break down in some of these other sets of operations, like we get to the jumps, for instance. But for now, let's go back to our opcode table And we can see how this works out. So that here, like, we have no ops, and we have, of course, 00 would be the general no-op opcode. Like if you put a no-op in your assembler, that's what it should generate, is like a 00. But if you were to just place machine code opcodes into memory, then any of these will do it, but some are going to work differently. So like if it's opcode 04 or OC, 05, OD, those are actually going to move the program counter ahead by further expecting there to be arguments. And in fact, I should have put this in here. Usually I'm better about this in the rest of the document. So that, yeah, if it's 04 or OC, there will be an argument that should be there but will need to be ignored. And this is similar to how sort of expansion spaces work on, say, the 6502, where, yes, they are especially that 65CO2. Yes, it's treated like a no-op, but because of the placement in the opcode table, the way it would be decoded, it's going to just fetch additional bytes as a matter of course. And so, again, these are side effects about injecting binary code, and it's not something you necessarily see while you're actually coding in the assembly language. So that we get through all the no-op opcodes, and now we get into the LoadA opcodes, starting with hex 10. And we can see here the first one's going to be a LoadA with 0. The way I'm setting up the mnemonics, I'm trying to keep most of the actual instruction name mnemonic to 3 letters, but making exceptions in certain cases, especially when we get to this 0 addressing mode, and to make it flexible enough to give the coder the option of either using this self-contained mnemonic of LDAZ for load 0 into A, or just using the standard immediate mnemonic and say just load A with immediate value of 0, but then interpreting it as this opcode instead of, say, this one down here, which would be the standard load A, where we'd have 14 for the opcode and then the argument for the immediate value. So, I mean, technically you could code in there in binary 14 and then 0, but generally the assembly would be smart enough that if you put 0 in there, it would just pop in this opcode, and that'll just optimize your code right there, because it's going to do exactly the same thing, have all the same results. But then, yeah, we can see the same thing here. Like we're going to have then oddities in there, like hey, load A into A. Well, what's that going to do? Not much. It's going to be kind of like a no-op. But here, what it will do is trigger some of our status bits. So if we come over here, we'll take a look at how these status bits are going to work. So here we're going to have a sign bit. So, and then every time you load into one of these registers, it's going to base these sign bit and this 0 bit based on what the resulting value is that's getting loaded into that register. So if it's less than 0, meaning that the high bit is set, so interpreting the 8-bit value as 2's complement would make it negative, that's going to be the sign bit. So we're basically bit 7 set. And then if it's 0, then we set the 0 bit. So obviously the load A was 0, that's what this instruction is up here. That's a good way to not just make sure that 0 is in that register, but we'll also set these bits to a known value of 0 for the sign and 1 for 0. So very simple. And then we'll see how some of the other bits work. But here we go. We see all the rest of the load A instructions, and then a special load A is going to be the pull A, where it goes into A is where the stack pointer was. And then on top of moving the program counter ahead by 1, it also adds 1 to the stack pointer, because we're pulling it off the stack. And like the 6502, we are we're starting the stack pointer at the top, at the furthest point in memory, and going backwards in memory, so that here, say when we push A, we are decrementing the stack pointer. And again, we can put the stack pointer anywhere because it's 16 bits. And yeah, so here now we can see once we get through this, we get from hex 10 to hex 17. Those are all of the LoadA instructions. Then from hex 18 to 1F, those are going to be the store, because here this is 1 for the upper nibble, and then here the upper bit of the lower nibble, bit 3, is set. So these are going to be storing from A. Now here we look at the lower 3 bits, storing A into the immediate value 0. That makes no sense. So in this case, this is going to be a special instruction where we are going to cut it off and say, nope, this is an illegal opcode. We won't do this. If we do see it, we'll treat it as a no op. And of course, in reality, I'm sure my initial implementation will just do whatever. So it'll probably start out like the original 6502 and eventually end up like the 65C02, where it gets rid of all the weird side effect behaviors. But who knows? Sometimes people like those weird side effect behaviors. But anyway, going back here to the table, now if we're doing store to register, that, of course, would be those next 3 addressing modes for store A. And obviously storing A to A, B, or C doesn't make sense because we already have load A into A, and we're going to have load A into B and load A into C later in the opcode table. So that's why we say here, well, in this case, if we're going to have 1, 2, or 3 in there, we're going to do a comparison. And now that I'm looking at it, why don't I just have a compare with 0? I don't know. I might just go ahead and add that add that in here, where I'm say comparing A to 0. So I could do something like, hey, CPAZ, and then say that the 0 result will be if A equals 0. I'm going to kind of leave that in there. So maybe that's what I'll do in these cases. And then, of course, like I do in other cases, I can make a fake immediate, because I don't have a real immediate compare. But you know what? Actually, I could. Why don't I just do that? You see, now when I'm talking through it, this is when things make sense. So I can do the same thing here, where I could do compare A to N, and then set 0 if A equals N. Or, so just A equals N. And yeah, so that's what I'll do here. And then the same thing here. A is less than N. So the sign bit will be set if A is less than the value that you're comparing it to. Is 0 bit is set if it's equal, and the carry bit will be set if it's greater than or equal to. So that's kind of how all these are going to work. Why do I have this store to register immediate? And I'll just make this smaller because I don't want to wrap things. There we go. So storing to a register or immediate is going to be a comparison. So what I don't have then in the instruction set is doing a compare to a absolute address, a direct address, because we have these general purpose registers. If we want to have a variable to compare it against, we're just going to have to load it into, say, B or C. and then you can compare it in A, or whatever. You got 3 registers that you can load values into, and then you can compare it with one of the other 2 registers. But then otherwise here we have really the only 2 kinds of stores that we can do is storing to that address or storing to the address that's in BC. So that's our way of doing an indirect store. And you can see here in these actual stores, like we would expect, if you do a store, it is not going to affect any of the status bits. And then once we get further down here, you see we're going to have all these different jumps. We're going to have unconditional jumps. We're going to have using the sign bit, the 0 bit, the carry bit. Use those 3 to jump based on there. I don't have like an overflow bit. So we're just going to be jumping on those 3 cases. And for doing we can't obviously jump to an immediate value. So in that case, if we are going to have the 4 here for the destination that we're jumping to, we'll interpret that as relative, and then also invert the state. So we could do like a jump if not 0 has to be relative. It can't be an absolute address because of where it sits in the opcode table. There's only going to be a single byte being fetched for its argument. And then here the option, instead of being to or from, it's going to be a permanent jump, just a straight up jump, or it's going to be a jump to a subroutine. So we're going to get some of that goodness that you get with the Z80, where you have these conditional calls, as it were. So, but kind of sticking to my 6502 proclivities, I'm calling them jump and JSR for jump to subroutine. And then here we can see all these different conditional ones where the unconditional jump, unconditional jump to subroutine, and then here jump if non-zero, and that's going to be the relative, and then jump if 0 to the absolute address, or jump if 0 to the address that's in BC. So again, using all of these the same, but then jumping to the stack pointer, that's kind of a weird thing. We're not going to want to do just jump to whatever's in the stack, to pull something off a stack and jump to it, because that's basically what a return is. So we have a different spot in the opcode table for return. But who knows, maybe it'll make sense to put it there. Again, none of this is set in stone. As you can see, I'm changing it as I'm going through. So those are all the different ways to jump. So we have effectively 4 times 16, so 64 different jump opcodes, because that's the kind of flexibility that I want, and the simplicity in the instruction set. And although, it's of course 64 minus these ones that I skipped here, where these are illegal opcodes. But again, I may find something to put in these opcodes later. Like, who knows, maybe I will stick those returns in there, especially when we're dealing here where the addressing mode is the stack pointer addressing mode. And then we have our math instructions. We're going to have add and subtract, shift left and shift right. And then the options will be with or without carry. And so we'll have, just like we have in Z80, the ability to do an add or subtract and not take the current state of carry into consideration, but always outputting to carry. The same thing with the shift left and shift right. We can say we're not going to bother with carry. We're going to shift 0 in. But if this one is set, then okay, this is going to be a shift where we're shifting the carry bit in to do the fill. And so that's how we'll get rotate left and rotate right. And then here with our logic, we're going to have a lot of different logic instructions because, again, I'm keeping it simple. And again, you may not necessarily have a use that you could see for all of these, but we're going to have the basic OR and exclusive OR with all of these different source and destination. Or in this case, it's going to be the source value for doing that. So we're, just like with the math, we could add in 0 or we could OR in 0. And then we could take in any of the registers, an immediate value. But the one thing we can't do, as we see here in both of these cases for math and logic, is that we can't do the stack pointer. We're not just going to pull something off the stack to use as an input like we would for load. So that's where we can get these other math logic instructions. So it makes an easy place when we have we have these math or logic operation codes up here in these in the upper nibble. If then we have the bottom 3 bits set, that will say, okay, we don't use the stack pointer in these. Here we can say that these 4 bits here, bits 6 through 3, are determining the operation that we're going to do. And that's where we fit in things like increment, decrement, and then having, I think, useful logic operations like negate and invert. So negate is arithmetic, where we're basically subtracting a value or subtracting a from 0, so we're just changing the sign. And then invert, which is a bitwise inversion of all the bits in any of those 3 registers. And then, of course, we're going to have the decimal mode. So we're going to have built-in decimal support. So we're enabling and disabling decimal mode, and that will take effect on particular math instructions. And then we're going to have the push and pull for that status register, because that's something that we're already going to implement in hardware for interrupts, but we're going to have that in an ability to do that in code too. If for some reason you wanted to keep status bits on the stack, or push a arbitrary value to the stack and then pull it into the status register just to set a particular state. And then here we can see that we finally get to the opcodes where the upper nibble is 15, or all ones, and that's going to be sort of the extra grab bag. So here it says here, if we have 14 or 15 in here, that goes to the other general, and that's where we have all of these single byte opcodes that do very specific things. But in some cases, we are going to add in the ability to have arguments. So, but that's where we're going to enable and disable interrupt, and return from subroutine, return from interrupt. We're going to have a halt until interrupt, which is like the wait instruction on 6502. We'll have a break instruction. We'll have a soft reset instruction, so that will execute that reset vector. Then here we're going to have one of these opcodes where we are going to actually load the stack pointer with an immediate value, so that will have a 2-byte arguments coming after that. And then, of course, being able to load the stack pointer from the BC register, or indirectly from the address in the BC register, and then be able to go back the other way is to load the stack pointer into BC, so you can do some fun stack manipulation, because what's the fun of having an 8-bit computer if you can't manipulate the stack? And then instructions to explicitly clear and set the carry bit and nothing else, and then some extra space for some further expansion. And that's it. That gets us all of these instructions and lets us do this. A lot of things that you normally can't do, like here, if you'll notice with the logic operations, we have normal and inverted for all these. So yes, you have a bitwise NOR and a NAND and a XNOR. And so, yeah, it doesn't make sense to generally include these because not a lot of programmers would necessarily use them. But for especially for embedded applications, there's a lot of use for some of these different logic operations. And just by allowing our instruction set, the actual opcode structure for that instruction set, by having that there and having this different mode bit already defined in that place, it makes it easy enough to say, all right, well, we're just going to invert because we're going to have the circuitry there, the virtual circuitry, to invert register values. So why not just use that? So yeah, it's going to be give you a lot of interesting capability that that your legacy 8-bit processors aren't going to have. But the main thing is keeping it simple. So yeah, like you notice, there's no bit testing instructions. We have that the limited number of compares. I got rid of overflow bit. There's a lot of things that are in some of these 8-bit architectures, which may be good for particular things, and were certainly useful when we were dealing with discrete logic back when these were individual chips on a PCB. But this is being made specifically for FPGA solutions, and that the single board computer that would be built around this would also be mostly in FPGA also. So yeah, we're not looking at creating a new discrete processor that we're going to plug into an old board. We're looking at just more of a fun, like, what if scenario. What if we had the ability to make 8-bit processors in a very particular way and to make it so that we're just trying to crank through as fast as possible through these instructions and not have to worry about a lot of the logistical matters for these old processors. And that's it. That's all I got. I know I've rambled on for a long time. I'm not going to do a ton of editing for this video, but I do want to make sure, as always, we shout out to the patrons of this channel, because they make it possible for me to do silly things like this and to spend time and money into making things like an 8-bit instruction set that maybe nobody else other than me is going to use. But I put it up. I'm going to be putting it up there for all the world to see and play with and contribute. And if you have any ideas, please let me know in the comments. And if you like this video, you want to learn more about it, make sure you click that like button and subscribe and click the bell to be notified. And if you're one of the patrons like these folks here, you'll get early notification for videos when they're done ahead of time, and get to see them before anybody else and have a real influence on how my content turns out and what I end up making videos about, and maybe even some of the games and other tools that I'm making. What makes you want to make something when I'm creating something that aligns with that? What is going to make you inspired to go out and create something for yourself and share with the community? Obviously, that's what I'm really about, building that community and getting folks to make things and share things and work together. All right. And that's it. That's all I got for today. So I bid you goodbye, and I will see you again soon.